Swayam Prabha. Digital India. Educated India.
So, last class I was discussing about the elastic theory method to check the stability of oil, and I have already discussed that one condition. Okay. So, that condition is this one, that your H should be greater than m by r 1 plus mu dash minus mu w, or H should be less than m by r 1 minus mu dash 1 plus mu w. Now, these are the values, and I have discussed what are these values. Now, the next condition, that for the stability condition, for example, that condition. So, you can see that this oil is rotating in from left to right side, okay, or you can say it is rotating in clockwise direction. So, that means that both side there are soils. So, one side will be passive, another side will be active. So, similar to that I have discussed in during the Tazaki's analysis. So, here the right side will be the passive condition and left side will be the active condition. So, if I draw that condition, suppose this is the original position of the well, and this is the rotating condition of the well. Okay, so, this side will be the passive and this side will be active. So, and the total throughout the depth in the right side is passive and total left side is active. So, the net pressure that will act here is K p minus K a into gamma into y, or a gamma dash I can say. So, into y. So, that means here if I draw the net pressure diagram, so this will be something like this, and this value will be equal to K p minus K a into gamma, and if it is d, so this is d, or gamma dash means the effective. So, this will be the net pressure diagram. Okay. And in the previous analysis, that means the Tazaki's analysis, the K p and K a was the Rankine earth pressure coefficient, but here it is Coulomb's earth pressure coefficient. So, K p and the K a. So, this K p and K a are the earth pressure coefficient. One is passive, one is active, as per Coulomb's theory. Okay. In Tazaki's analysis, it was as per Rankine's theory, but here it is as per Coulomb's theory. So, as per Coulomb's theory, so we know that P value or the net pressure or the passive force that act at an angle of delta to the vertical face. So, this will act with an angle of delta. So, this is net P net. Okay. So, that will act with an angle of delta. So, for the stability condition, so we have already drawn this pressure distribution diagram. So, that means this sigma x. So, sigma x expression is given. So, here sigma x is this is kilonewton per meter square. Okay. So, this sigma x that is acting, that should not be greater than the net pressure. So, you can see that this is the sigma x or the horizontal stress at any point y. Okay. This is the horizontal stress at any point y. So, that is acting at this point, and there will be a net soil pressure. That sigma x should not be greater than that soil resistance. Suppose if that sigma x, which is the horizontal pressure which is developed, if that is greater than the soil resistance, then this well become unstable. So, to make this well stable, that the stress, horizontal stress which is developed at any depth y from the scour level should not be greater than the soil resistance at that point. So, in that condition, the soil resistance at that point, say at a depth of y, say will be K p minus K gamma dash into y, and it is acting at an angle of delta. So, the horizontal component will be cos delta. Okay. So, horizontal component will be cos delta. So, sigma x should not be greater than this value. That means, this is the stress developed and this is the resistance or soil resistance. Okay, and this is the stress developed. So, that means, this should not be greater than the soil resistance. So, if I put that condition, now sigma x value is given. So, this is the sigma x, which is m k v theta by d minus y into y. So, if I write that sigma x value, so this will be m k v theta by d into y d minus y, that should not be greater than K p minus K a into gamma dash y cos delta. Okay. So, or further we can write m k v theta divided by d. So, y will cancel out and d minus y should not be greater than K p minus K a gamma dash cos delta. So, this value, this left hand side value will be maximum. So, this is maximum. So, the maximum at y equal to 0, this right side value, this value will be maximum because y has been cancelled out. So, now this value will be maximum at, it is not the stress, I am talking about now the current left side value. So, this should be maximum at y equal to 0. So, I can write that m k v theta divided by d into d should not be greater than K p minus K a gamma dash cos delta, or I can write that m K v theta should not be greater than K p minus K a into gamma dash cos delta, or I can write that K v theta is what? K v theta is equal to m by I. So, I can replace that K v theta by is equal to m by I. So, this is m small m into capital M by I should not be greater than K p minus K a gamma dash cos delta. So, this is another condition. Okay. Condition 2. So, we have to satisfy this condition also to maintain the stability of the well. Okay. Now, we have one more condition, that is the vertical soil resistance or soil reaction, I should say. So, this is condition 2. So, next condition is vertical So, that means that the stress which is developed at the base, that we have to also check. Okay, so, now how we will check that? So, the stress, vertical stress at any point sigma y is equal to K v theta into x plus x c. Okay. So, vertical stress at any point, sigma y is equal to K v theta x plus x c. So, this is vertical stress at any point. So, now we can write that W minus mu dash p, that is the total vertical downward force. So, this is W minus, so that means what are the vertical force? W is acting downward direction and mu dash p is acting vertical direction, I mean upward direction. These are the two only vertical force. Okay, so, wait, this W which is acting in the vertical direction, you can see this W is acting in the vertical direction. Okay, and this mu dash p, that is also acting in the vertical direction, but both are in opposite direction. So, that vertical force is W minus mu dash p, that should be equal to the summation of the soil reaction which is acting at the base of the well. So, summation of the soil reaction will be the vertical stress at that point sigma y, and if I integrate it over the area of the base of the well, then I will get the total soil reaction. So, this is the total soil reaction, and that should be equal to the downward or the net downward force, vertical force. So, sigma v I can, sigma y I can replace by K v theta x plus x c, and this is dA. Or further we can write that K v theta into x dA plus K v theta x c into integration dA. Now, I have already discussed that this part will be equal to 0, because your CG is the center of the base. So, that means here integration x dA, this part will be 0. So, if this is 0, then this will be simple K v theta x c and dA will be equal to A. If I integrate the small area, then that will be the total area of the base. So, this is the where A is the area of the base. or this is definitely outside area. Okay, so I can write that kV theta xc, that will be equal to W minus mu dash p divided by A. Okay. So, again I can write sigma y is kV theta x plus kV theta xc, because this is the sigma y, and that sigma y is the stress, vertical stress at the base of the well. So, that I can write that, or I can replace this one, this is sigma v theta x, and now kV theta xc is equal to W minus mu dash p by A. Okay, I can replace. So, I can write that sigma max or mean, that will be equal to W minus mu dash p by A, then plus minus. Why plus minus? So, there are two ends. This is the plus b by 2 point, this is minus b by 2 point. So, I should write this is minus b by 2 point, this is plus b by 2 point, because this is the width. Okay. So, if I put these two limit, because we definitely the maximum stress at the base and the minimum stress at the base will be at two edges of the well. So, that is plus b by 2 minus b by 2. So, this will be plus minus. Now, b by 2 where I will write? I will write this is kV theta, in place of x I will write plus minus b by 2. Okay, because this is the x which is at the distance from the center. We can see that x is at distance from the center. So, that I can write plus minus b by 2, or further I can write that sigma max mean will be equal to W minus mu dash p divided by A plus minus. Now, kV theta is what? kV theta is m by I. So, again I can write this is capital M by I b by 2. So, this is another condition, or by this we can calculate what would be the stress which is acting at the base of the well, or I should write this is condition 3. There are two conditions. If I put plus, there will be one, if I put minus, there will be another, but that is maximum minimum stresses. So, these are the conditions. These three conditions we have to check as for the elastic theory method for the stability of well. So, this is condition 1, this is condition 2, and this is condition 3. Okay. So, this is one method, that is elastic theory method. So, next method that I will discuss is the ultimate soil reaction method. So, ultimate soil reaction method is another method by which also we can determine or we can check the stability of the well. So, in this method, so as per this method, the load combinations and the load factors, those are recommended, are as follows. So, what are those load factors? So, here the different loads will act on the well. So, these loads are dead load, live load, buoyancy force, then water current force, earth pressure force, because both sides will be soil, then wind force and the seismic force. So, and then the load combination that we have to consider during the design or during the check, that dead load alone, dead load live load, dead load buoyancy load, then the water current, earth pressure, wind load or seismic load. So, it is quite uncommon that the seismic force and the wind force will act at the same time. So, that is why it is taking either wind load or either seismic load. Then next combination is 1.1 D plus B buoyancy force, then live load, earth pressure load and the water current. And then last one is considering all the forces, the dead load, buoyancy load, live load, water current, earth pressure, wind or the seismic force. Okay, so now here different load factors are recommended. So for the dead load, this 1.1 is the load factor. Why? Because the more or less dead load is a permanent type of loading. Okay, so that's why here load factor is 1.1 is suggested. Now, when the live load is added to the dead load, the second combination, there the with live load 1.6 load factor is recommended, because that this is due to probable overloading. So, now if we add dead load and live load, this is due to probable overloading. So, this load factor is applied. Now, when this live load is applied with the other forces, that means you can see that for the last combination, when this live load is added, when it is added with dead load, this is 1.6 is the load factor. But when it is added with the water current or earth pressure or wind load and wind load, then it is 1.25, because it is very uncommon that when there will be a wind load or the seismic load, and in that time there will be maximum amount of live load will act. So, that is why that the reduced probability of occurrence of maximum live load when the wind load and the seismic load is acting. Okay, that means when the wind load or seismic load is acting, there is a very rare probability that the maximum live load will act at the same time. So, that is why a lower amount of load factor is suggested. But for the buoyancy, the load factor is taken 1, because because of the buoyancy, the reduction in the density of the submerged masses is more or less constant. So, that is why it is taken 1, and when this live load is added with earth pressure and the water current, but not with wind or the seismic, in that time it is higher than the wind, when the wind load and seismic load is considered, that is 1.2, it is more than 1.2, but it is less than 1.6. So, it is 1.4 is added, because that is sufficient, because all the cases this 1.4 is sufficient, because this reduction of the load factor is due to that occurrence of all the maximum forces at the same time will reduce as you consider more number of forces at a time. So, that is why these are the different load combination that you have to consider during the design, and these are the different load combination and the corresponding load factors are recommended. So, next one is that for this particular method, that we will consider that this is the well So, this is well and this is the scour level, and here the H is acting in this direction. Okay, this is the center line, this is B, and this one is the depth of well below the scour level. And here, as per this method, it is assumed that this well will rotate with a point, and say this point is this one, and that point is at a height of ND from the base of the well, and when it will rotate, then this well will rotate along this within the soil. So, there will be a rupture plane will develop below the base of well. So, with a radius of r, we can draw this rupture plane, okay, and the theta, this radius is making with the vertical line the angle, that is theta. So, along this rupture plane there will be a shearing will occur. Okay. So, this is the rupture plane. Or rupture surface. Okay, and if you say this is the vertical force or the normal force along this rupture surface is F n. So, this shear force or shear stress will be F n into tan phi, because it is the friction between soil and soil, because the rupture surface is within the soil. So, it is rotating, because of this rotation of the rupture surface will be developed at the base of the well. And if the F n is the normal force normal to the rupture surface, then the shear stress that will develop along this rupture surface will be phi n and or F n into tan phi. Phi is the friction angle between the friction angle of the soil. Okay. Now, if the cross section of the well, say, or rectangular cross section, then again this is B and this side is perpendicular to that sectional view, that length is L. Now, if I draw that rupture surface portion only, if I draw the rupture surface portion only, so this is the point and this is the rupture surface, which will be a circular path. So, this is rupture surface, this is the center line and this angle is theta. So, a small segment is considered. Okay, so, this small segment is considered at an angle of alpha, and this angle is d alpha. Okay. So, at an angle of alpha we have considered a small segment which is angle of d alpha, and this is the width of that well. Okay. Now, the applied load or the load which is, so we have a applied load of W. So, W is acting here, the downward load. So, here that applied load is acting at the base, or at that applied load is this one. Okay, so, that will be W by B is written here. So, that is the applied load. That is the applied vertical load, and there will be a upward base pressure. So, base pressure will also act, okay, below the rupture surface. So, this is the upward base pressure. Okay. And as I mentioned, there will be a vertical force along the rupture surface. So, that vertical force for this particular small segment is dFn. So, this vertical force is basically perpendicular to that rupture surface. So, these are the forces are acting at this small segment. Now, let us determine that how we can do the stability checks for this particular condition. Okay. So, there will be a force which is acting dFn. So, now we can write that the vertical component of force on the element which element, suppose we have considered a element which is a very small element, say like this is the element that we have considered. So, this is the element that we have considered. So, and on that element the DFN is acting, okay? DFN is acting on that element. Now, what is the force which is acting on this plane? Suppose if I take, say, this element, if I take horizontal and vertical, and then how much, what is the vertical component of force on that element? So, that means the vertical component of force. So, this is the normal. So, vertical component of that force on this element. Okay. So, that will be the total, that forces will be, this is R and d alpha. So, that is the element. Okay. So, what will be that element length? So, this is the R is the radius and angle is d alpha. So, the length of the small element, so this small element, length of the small element, this element, okay. So, this small element length will be d r d alpha, and we are taking the vertical component of this element. So, or we want to calculate the vertical component of the force on this element. So, this horizontal component of this element will be cos alpha. So, this is the element, horizontal component of the element on which the vertical force will act. So, that horizontal component will be R d alpha is the element, and horizontal component will be into cos theta. Then the vertical applied load which is acting, W by B. Okay. So, this is the total vertical component of the force. Now, thus the normal force, because why you have taken vertical component, because your W by V is acting vertical direction, but your direction of the element that you have taken is not horizontal or vertical, it is with certain angle. Okay. So, that is why the horizontal component of that element, you can say, on which this vertical force will act. So, that is why we have converted this element with d alpha into cos theta. So, that will, on that portion this vertical component of the force is acting. So, that is why in the horizontal component we can write directly that what is the vertical component is acting, or vertical component of force is acting on that element. Okay. So, this is the vertical component which is act on the horizontal component of that element. So, thus the normal force developed at the element due to vertical force will be equal to, now this is the vertical component, again remember that this is the vertical component of the force on the element, but we want to determine the DFN. Okay. We want to determine DFN, which is the normal component of the original element. So, that means that DFN, we know the vertical component, now the DFN is the normal component or normal force. So, again we have to multiply with cos alpha. So, then we can again convert it to vertical to normal. So, initially we convert this to that, why we have converted it to vertical, because our load is acting vertically. So, that is why we have taken the vertical component, then now we are converting the vertical component to the normal component, because that force we want to determine. So, that means again this will be W by B R d alpha cos alpha, this is the vertical component, then again cos alpha, this is the normal component. Okay. So, now we can write that f n will be the integration of from 0 to theta. So, f n is the total force, this total normal force along the rupture surface. Okay. So, that will be 0 to theta, and W, or I should write 0 to theta W by B R cos square alpha d alpha. So, this is for the one half, but we have other half also. So, that means this will be 2. Okay. So, this is the total normal force along the rupture surface. So, we can write, if I integrate this, then put the limit, then you will get that R W by B theta plus sin theta and cos theta. So, this is the total normal force that is acting along the rupture surface, and if I multiply with that f n with tan phi, then I will get the friction force that is acting along the rupture surface. So, next class I will continue this part, and I will show you that how we can convert this theta with the other parameters like depth of the well or width of the well, because these parameters, depth of the well, width of the well, so these are known to us. So, we have to ultimately convert this theta to that parameter. So, those things I will discuss in next class. Thank you.